Before that, okay. So before this, we are looking at linear regression as a function of two variables. For example, y equal to ax1 bx2 plus c. So a, b, c are the three parameters to be retrieved. So we can just take the sum of the residuals using the least square funda for n points I equal to 1 to n. Y data yi minus y fit I whole square. Then you just take dou s by dou a equal to 0, dou s by dou b equal to 0, dou s by dou c equal to 0. Solve for three unknowns. So I've set up 5 equations. Equation 1, 2 to 5, and solving 3 to 5. You can find out ABC. What is the motivation for doing this? There are many correlations in fluid flow and heat transfer which are like this. For example, the famous Dittus-Boelter equation. NUD is 0.023, Reynolds to the power of 0.8, Prandtl to the power of 0.4. Prandtl to the power of 0.4 if the fluid is getting heated. Prandtl to the power of 0.3 if the fluid is getting cooled. There's a famous correlation for getting the average Nusselt number, that is a dimensionless heat transfer coefficient for a fully developed turbulent flow in a circular pipe. Okay, so Reynolds number based on D. From NU you can do NUD is HD by K. Okay, if you know the Reynolds number and the Prandtl number, if you know AMN, you can use it in this correlation and get NUD. From NUD, you'll get H. Once you get H, you can use Newton's law of cooling and get the heat transfer rate, which is the goal of studying heat transfer. Okay. Now, if you take the ln of NUD, this will be ln of A plus M ln RE plus N ln PR. Okay. So if you have a data, if you've got a table of various values of NUD for combinations of RE and PR, you'll be able to get AMN. You have a correlation, then you can find out what is the R square of the correlation, what is the standard error of the estimate of the Nusselt number, all that you can find out. This is how correlations are developed originally, and these are called as empirical correlations. Please note that essentially they've solved an inverse problem, but in this case the forward model is the proposal. The forward model is not a differential equation. You should not think that an inverse problem is one in which the forward model is always a differential equation. This can come from a differential equation for CFD and heat transfer for this flow. That's beside the point. Okay. But the funda is, if you put it in this form, then it's possible to get AMN. Like that, there are several other correlations. You can have another parameter, which is the viscosity correction. You can have, for example, it could be a rectangular pipe, in which case it could be H by L aspect ratio. It could be an elliptical pipe where A by B could be aspect ratio. You could keep on doing this. So this is called a power law form. It's called a power law form. Okay. So this is very popular in heat transfer. Now the whole game is, if you go to the heat transfer lab and generate a lot of data for various values of Reynolds number and Prandtl number, for various values of Nusselt number, from the experimental data, you can use your principles of regression. You can pose it as an inverse problem, get A, B, C, and be done with this. This is the way Dittus and Boelter did, but they never thought about this idea of an inverse problem and all this. They just fit they just did a fit to this. Now, it is possible for you to go to ANSYS Fluent or COMSOL, star CD, OpenFOAM, write your own code, Fortran, C++, Python, or whatever. Solve the problem of a turbulent flow in a pipe or a duct. And then for various Reynolds number and Prandtl number, you can generate the Nusselt number. So this data could be based on simulations. This data could be based on your own experiments. In any case, once you come to this level, it is a data-driven approach. It is a data-driven approach. Now, what the data science people will be saying is, regardless of whether you are doing the experiment or not, whether you're doing the simulation or not, if you had access to this data, if different people conducted experiments on different pipes, with different Reynolds numbers and different Reynolds number and different Prandtl number, it should be possible for you to synthesize using this, which is perfectly fine. But in an engineering subject, who is going to give you the data? That is the first question. How reliable are these data? Okay. So it may apply in consumer behavior, this thing, and for pure computer science approach, it may be work. But if you want to work it in apply it in hardcore engineering problems, so you have to track the original source of data and then see whether, and who will tell you that the Nusselt number is a function of Reynolds and Prandtl? Only heat transfer person can say. First, to find out that because the experiment will be done for various diameters of the pipe, various lengths of the pipe, various viscosities of the fluid, various temperatures, then there will be too many data. If you're just a data science person and computer science background, whatever, you don't know any heat transfer, you will not even come to this. Please know a lot of intelligence is required to come to this level. Okay, you need to get to the just by blind this thing, you can't get it. Okay, so how to get this form? Either you should be put in the theory or get it from literature, or you should be able to do a Buckingham Pi theorem and write in terms of dimensions and find out what are the governing parameters which are governing this. That is the second approach. The third approach would be to take the original governing equations and keep on normalizing them. If you keep normalizing them, you will hit a point where there is a this Reynolds number and Prandtl number will automatically come into the picture. Okay, Reynolds number and Prandtl number will automatically come into the picture. Otherwise, you will just correlate. There will be a lot of input and output. How will you know that whether the inputs are correlated, whether the output is, whether the inputs are independent and all that? So just with pure data, you can't do much. Okay, in some fields it is possible. Okay, but a fellow who knows heat transfer, a person who knows heat transfer will use minimum data and get the maximum out of it. Okay, so that's why. But if you know data science, it helps. If there is a factory, or if you are a heat exchanger company, you've got a lot of this data, then it's possible for you to use your heat transfer principles as well as data science to come to solve this problem. Okay. Okay. Now there are other forms. Okay. Before that, for example, other forms. One second, I'll try to find out who is trying to call me. 5708 is who? See, because somebody will simply not know whether I'm taking a class or not, because the office room has become the classroom. Suppose we were in CRC and you came to the classroom, I went to the classroom, they wouldn't call. They won't know that if somebody is not lifting the call, he's in a class or he's. No, they persist. No, that is a problem. They persist. Even if I don't take, they will again call. They will again call. Okay. Other forms which can be linearized. Okay, so y equal to ax to the power of b, we saw that. So ln y. Okay. Then can you linearize this? Can you linearize this? How do you do that?
Apply a ln.
Yeah, apply ln. Please do that. Yeah, apply ln. Who was that? Yeah, no problem. Who was that? Have you done it? Okay, ln plus b. What is this? It is b. Can somebody respond?
X.
Bx. Very good. That's it. So this one. This frequently occurs in transient conduction. We'll see that tomorrow. It frequently occurs in transient conduction. It's a lumped capacitance model. Can you do this? So how will you just go ahead with linear regression? What can you do here? Yeah. Anybody? Somebody should respond. Can we linearize? Hello, am I audible?
Yes, sir.
Okay. What should we do? Can someone respond?
Take ln.
Take ln. Very good. Okay. Great. Is it fine? Okay, just think about this.
It becomes a function of two variables, sir.
1 by y and 1 by x, sir.
1 by y. Okay. So before saying that it becomes a function of 2, take 1 by y. Is this okay? So we can keep on solving some puzzles. So I know you like this, we can keep going on, but we have to stop somewhere. But don't think that all forms can be manipulated like this. Some forms it's possible to manipulate. I think this is fine, right? I didn't make any mistake, all right? So if you can manipulate, try y, try 1 by y, try ln y, try y minus 1, y plus 1, 1 by y minus 1, 1 by y plus 1, whatever tricks, try all the tricks and find, but finally you should be able to get it. Right side somehow should become a straight line. In the left side, it should be possible for you to relate it to the original this thing, and it should be y equal to ax plus b. All right. All right. So there are some forms which even if you turn upside down, okay, you go to Himalaya and do meditation, you will not get it. Okay. That I will tell you later, not now. Let it be a suspense now. What is that form which cannot be done? So that will lead us to what is called nonlinear regression, but not now. Hold on. We have to do some more work to get there. So is it okay? So even with linear regression, we can do some magic. We can do some manipulation. We can have some fun. Not just fun. There are some heat transfer forms. I told you. I am giving you, see, this course is inverse methods in heat transfer. It is not a course in probability and statistics. So this is lumped capacitance, turbulent flow. If you see, I am not just focusing only on the technique. I am telling you what is the heat transfer problem which you can relate to. Okay. That is why things are taking time. It's going a little slow, but I think you'll be able to appreciate that. Appreciate how we are applying these principles with thermal sciences. Once you learn the application to one subject, on your own, you should be able to learn it and apply it to any other subject, whatever be your subject of study, your subject of work, or your passion later on. Okay. Doesn't matter. Well, let's go to, it's fun, no? Okay. So we already spent 15 minutes. Please remember that before I logged in, I wrote this. It was taking 15 minutes for us to get back to this polynomial regression. So there are two options available to you. I can give you the polynomial regression form and tell you where it is applicable in heat transfer. Or we can do what is called the flipped example approach, the example first approach, where I'll tell you where in heat transfer we'll get a polynomial form. And then we'll do the regression. So which do you like? Huh? So which do you like? You tell me. I can change the discourse accordingly. Huh? Huh? Hey, somebody should respond. When you all had breakfast, right?
Lived one.
Huh?
Second one. Second one.
Second one. Okay, very good. No problem. Okay, consider so consider a 1D slab of length 2L. So it is semi-infinite. So it is infinitely long. So let it start at x equal to 0 here. So this is L. This is L. Okay. Let us say that K, rho, Cp are all constant. However, there is a heat generation within the slab. QV is not equal to 0. QV is not equal to 0. Okay. To make it simple, I will say that the surface is maintained at a temperature of Ts, both sides. Actually, what it means is, it is bathed, both the sides are bathed by a fluid, which is at T infinity with such a high heat transfer coefficient that the T infinity becomes equal to Ts. Those conditions we can see a little later. Okay, so now let us make some assumptions. So is the situation clear? Just copy down this figure. Oh, I wrote as. Okay, sorry. So you have to write assumptions. Can we proceed? Oh, Akula is writing to you. Please. Okay, he's saying, please fill up the attendance. Can we proceed? Somebody should do a thumbs up. Okay, fine. Okay. Now assumptions. T is a function of x alone. QV is not a function of x. QV is not a function of t. K, rho, CP, constant. P is not a function of time. Once you say something is not a function of time, it is steady state. Okay. So now the governing equation. So please note this in inverse methods in heat transfer. In the quizzes and exams, we will start from this. I cannot teach you the heat transfer again. That is why it is given in 6th semester so that 5th semester or 8th semester students can take it. But it is open notes. It is open everything. You are going to write the exam from your home. Okay. Take any heat transfer book. Take the whole. You take go to any library, pick up any book. Take your own heat transfer note. Watch MIT lecture. Watch NPT lecture. Whatever. But you should know what the governing equation is. Don't ask me in the exam, sir, what is the governing equation? Then the idea of this course is defeated. Then this becomes a course in only in probability and statistics. You're expected to know what is the governing equation for this. Okay, because all these assumptions are given. So now this becomes we started with the what is the equation number for today's class? I started with 1, 2, 3, 4, 5. Now just look at the notes.
8, sir.
8.
Manthan Patel, very good. 8. Okay, at least there is some response. So please note that. Okay. It is very simple. T is a function only of x. 0. This is 0. Okay. Okay. Before I forget, quiz at 12 noon on Thursday. Quiz 1. There'll be 2 questions. So you know the syllabus is up to what we have done last week. Linear regression, probability and statistics basics. 2 questions will be there. So slightly tricky, but it's okay. Not very. So 12 to 12:50 and up to 1:30 can upload. We have set up the question paper. We have checked the solution. All that we have worked out the solution. Everything is done. Question paper will be sent to you by email and WhatsApp 10 minutes before the exam. Okay, you will get it at 11:50 a.m. So this week, because it's good that we have it on a Thursday because you have the lunch break as a buffer. That's one. And suddenly the dean decided that 1 week there will be no classes. So if we have 2 quizzes on these 2 days, so essentially we miss only 1 class. So I will take 1 class towards the extra. Then we are doing good. There's no problem. And I think most of the classes we are doing the full 50 minutes. Sometimes it's 52, 53 minutes. So it won't matter. Once I take 1 extra class, we should be fine. All right. And the exam also is like class, right? Because there's no stress for you. You can even some of you will even exchange WhatsApp, this thing, whatever. Doesn't matter. But it is your work. You have to do it. Okay. It will be roll number specific. You cannot copy it from somebody. Because no 2 people will get the same answer. Okay. And since it is open notes, since it is an inverse methods course, since it is unproctored, lot of marks will be for 60 to 70% of the marks will be for the values. Don't tell me method is correct. I don't even know. You could have copied. Therefore, if there is a 10-mark question, only 4 marks for getting the algorithm right. The last 6 marks will be only for getting the answer right. You've got 40 minutes to check, recheck, re-recheck, whatever. Only if you, and that number is yours. No two people will get the same answer. Okay. Therefore, 60% of the weightage will be for the numericals. Okay. It is not an ideal situation, but under these COVID conditions, this is the only thing we can do. All right. Now, this is the best we can do. This is not the only thing we can do. Okay. Therefore, d square t by dx square plus qv by k equal to 0. That's equation 10. Okay. Integrating once. So please keep your heat transfer notes also along with you, whether you are in, if you have studied in some other college also, it's okay. You keep your old heat transfer notes. Okay. Our students, 6th semester, for half of you, I have taught, or one of my colleagues has taught you. 6th and 8th semester students, please keep your heat transfer notes. Suppose you just see what is that, whether it is steady conduction and steady conduction, what is that sphere, cylinder, this thing. So at least you should be able to get the governing equation. Or if you're that smart kid, no problem. Governing equation for steady state conduction with heat generation in a slab, this thing. Go to Google Baba and get it, no problem. I have no problem. You can get the equation from anywhere. But I want you to get this equation. Okay. So integrating once. Okay. Now coming to the boundary conditions. At x equal to 0, dt by dx equal to 0. This is actually called the symmetric condition, because both the ends are met at the same temperature. It's a uniform heat generation. Therefore, you expect the temperature to be the same. I mean, at x equal to 0, it should reach the maximum, right? There's somewhat, so you expect that symmetry, which is basically common sense. At x equal to plus or minus L, T equal to Ts. I think I will put Ts is okay. Surface, T surface. Okay. So this equation 12, equation 13. So just look at equation 12 and apply to equation 11. I come again. Look at equation 12 and apply to equation. What is the value of A now? What should be the value of A?
0.
Very good. Yes. Applying. Integrating again. Okay. Now temperature is a function of the quadratic function of x. So there is a motivation for a polynomial regression. Okay. So we'll complete it, and then where is the inverse problem? All that we'll discuss. Don't worry. Equation 14. Now apply the boundary condition here. This is 13. This is 14. This is 15. Applying 13 to 15. So Ts. That's it. Just copy this. Just check if I'm fine. So what you should do is you should do what is called a sanity check, correct? It's called a common sense check. If you're a good scientist or a good engineer, you'll always do sanity checks. So you'll do the sanity check at x equal to plus or minus L. We'll also do the sanity check at x equal to 0 to check whether the temperature is at x equal to 0. Anyway, you can't x equal to 0, dt by dx is 0. That you anyway get this. At x equal to L, you can check it. This term will vanish. Okay, so this is the solution. So if it's fine, you can just give a thumbs up. Or if it is not fine, you'll ask me a question. Very good. Okay. All right. So looks like it is like this. So that's the temperature. At x equal to minus L, temperature is Ts. At x equal to plus L, temperature is Ts. And it is symmetric about x equal to 0. That is why dt by dx is 0 here. And this, what is this fellow? Can you tell me what this fellow is? What is this fellow height?
Q square, QL square by 2K.
Exactly. Exactly. QVL square by 2K. What can you call it? Can you give it a name?
Sir, excess temperature.
Excess temperature. Exactly. So I will call it temperature excess. Can you qualify it further? Due to?
Heat generation.
Exactly. There you are. So all of you know heat transfer very well. So temperature excess due to heat generation. Very good. See, no need to mug up big books and this thing and write exam. You just start thinking. Take a paper and pencil and just after some basics are there, it is on. Everything is here. All these have come out. All these have come out out of Planck, Nusselt, Fourier, and this thing. Everything is here. Apples were always falling down, even before Newton's time. Okay. Please note that if Newton figured out gravitation at t equal to 0, at t less than 0, it doesn't mean that apples were going up. Okay. So he didn't invent the law of gravitation. He discovered. Okay. Invention is different. Okay. Invention of iPhone, invention of that is different. Okay. Laser, all right. Okay. So natural laws, it's discovery. Okay. Fine. Now, suppose there is a problem which is going on. Suppose it's a heat generation in a nuclear reactor or some chemical reaction is taking place, or there is a cancer in the body and there is a temperature excess compared to that. Or if the, so simple thing, fever in the body in COVID, they said no, fever in the body can be found out like this. Like that, if you take an infrared thermogram and then somebody has a tumor in the breast, okay, or a tumor in the uterus, or somebody has a skin cancer, or some lump is there, some tumor is there and it is generating, it's having a lot of metabolism. So there could be an instrument, which is an infrared thermometer, which can pick up the signature. So there'll be flushing of skin, and even when you do exercise, no, you feel that suddenly the body will get, you just jog for 45 minutes. Then there'll be a lot of heat which is generated. At that time, if you measure the temperature, it won't be 98.6 because you just sweated it out. Okay, so You've just worked hard. So your pulse rate, BP, everything is high. So now I just make some measurements here. Please note that if I make at minus 4 centimeters from here and 4 centimeters from here, it need not be the same because my thermocouples are all having error. There is a standard deviation, sigma square, all that is story is going on. So I have measurements. Okay. Now, so what is the inverse problem? Okay. What is the inverse problem? The inverse problem is T1, T2. I'm measuring. But QV is something I don't know. So if I know that QV is non-zero, suppose there is a clinical correlation, I can find out whether there is a tumor. I can go even further. Depending on the size of the tumor and the location of the tumor, the temperature distribution, that won't be d squared t by dx squared. I'll take a spherical coordinate. If we are modeling a tumor in a breast or something, we'll say r theta phi coordinates is better for that, and only surface we'll take. We'll take a hemispherical this thing. We can say that some lab or some doctor oncologist is just taking a infrared thermogram. You may ask, sir, how can't we do MRI? Infrared thermogram is cheap, inexpensive, it is non-intrusive. So straight away, all the people need not be referred to CT scan or MRI scan. So this can be used as a screening. Okay, this can be just as a, just like everybody need not go through the RT-PCR. Now airport, only suspected cases will be sent to, because MRI is expensive, time consuming, right? The MRI will be 8,000 or 10,000 rupees. So this, if you get an infrared camera, simply you can screen. If somebody is, everything is clean, there is no need for additional investigations, at least for the time being. Okay. Now the question is, if I have many measurements, can I get the QV? Now the problem can get a little more difficult. Okay. If same slab, okay. Now I say this is X. So I'm not, so this is 2L. So I forget about the symmetry for the time being. Now there is a fluid. So this could be heat exchanger. This could be some metallic wall separating two fluids. So let us say this is H1, T infinity 1. One fluid is flowing like this. So this is H2, T infinity 2. There is a QV which is not known. Okay. Now what I do is, at T1, T2, Tn, n measurements. These n measurements, suppose what is QV? This is simple inverse problem. Suppose, can you tell me what is QV H1, H2? This is a more tough inverse problem. Okay. Because now I'm saying that one, but I am measuring, I have a lot of data. I'm crazy about data. I'm a data scientist. I have a lot of data. Can you tell me? Can you believe that a simple data scientist can do this? You cannot. You will try to correlate, but you should know the mechanism, right? You should know the mechanism. You should know how many hidden layers you have to use. It's non-linear. Single hidden layer may not work. You may have to use a deep neural network. Okay. Or whether you want to use a convoluted neural network, all these terms which I'm telling now, Suresh Balaji will explain to you. So now there's no need for you. Don't get scared by what I'm saying. So whether you want to use a radial basis function or a backward propagation, whatever. So that depends on the knowledge of the physics of the problem. Okay. The harder problem could be when QV itself is a function of X. Suppose QV itself is A plus dx, or QV itself is A sine omega X, A sine omega X by L, for example, or something like that. It is periodic. So because there is a neutrons are doing this, so there's some nuclear fission which is taking place. Therefore, I know that there is more heat generation at the center compared to this. Then if this becomes linear, the temperature will become cubic. Okay. This is required in the nuclear industry. So they will tell you that I can measure temperatures of few places. I have this data. Okay. I have a lot of data, temperatures at these places. Now tell me QV. Now QV is also a function of time. So how much is the What is the heat generation which is generated because of nuclear fission? This will be a hard problem. This will be a, in that case, it won't be just d square T by dx square. This will be a cylindrical coordinate or a three-dimensional conduction problem as we solved. And see whether if there is convection between the various rods, you have to solve the CFD equation. So the forward model will be full three-dimensional, unsteady, turbulent flow with the Reynolds average, Navier-Stokes equation. There is a heat generation inside the nuclear fuel rods, and there is a convective boundary condition or insulated boundary condition on the outside. There is cladding, there is lead wall, and all that. There's a and millions of nodes will be required to simulate the forward model, and some measurements are available to you. You are trying to figure out what the cause of the failure is or something. So you are doing a failure analysis, or even you may be doing even a risk analysis. In that case, you should be strong in data science. You should be strong in heat transfer. You should be strong in nuclear physics. You should be strong in reactor physics, okay, neutron physics, and all that in order to crack this problem. Otherwise, if you are just a data scientist, we'll be like a quack. We won't know what is actually going on. There's so much physics going on. If you're able to combine the physics with the data, then you're on solid wicket. Now, there is motivation. So the temperature distribution is parabolic, quadratic. Therefore, there's a motivation for us to do not non-linear regression, but a polynomial regression. Is that okay? So I established the case for polynomial regression in a simple conduction problem. Now, for the third time, I'm writing the words polynomial regression on the same place at the backboard. Do you agree? Before starting the class? After starting? Now again, I'm revisiting. Okay. Now, let y be ax squared plus bx plus c. That is temperature equal to ax plus a squared plus bx plus c. But temperature equal to a r squared plus br plus c. We don't know if it is a radial coordinate, spherical or a cylindrical coordinate. For that, the governing equation 1 by r, dou by dou, r of RTD by dr, all that is there in your heat transfer notes. We have done that simple one-dimensional conduction in sphere and cylinder. All right. So y equal to ax squared plus bx plus c. Okay. Now, y1, yn measurements. Available. What is available? Data is available. Okay. Yes. Equal to sigma equal to 1 again. Yi minus a xi square minus b xi minus c whole square. Sorry, I'm again going to start with 1. Okay, because I lost track. So dou s by now the time is 11:42. You have 8 minutes. Just crack it. Just do dou s by dou a, dou s by dou b, dou s by dou c equal to 0. Class, please assemble all these equations and put it in a nice metric form. Sigma x square, sigma x to the power of 3, sigma xi y x square y square. All that will come. Do it now and keep it in your notes. Please do this. So this is the formulation of a polynomial regression problem of 3 constants, 3 parameters A, B, C. What is the motivation? All the time it happens in bioheat transfer where there is a cancer or a metabolic problem, or in a chemical reaction, exothermic reaction, endothermic reaction, Q will be negative, or in a nuclear fuel rod. Go ahead. I will keep quiet. 11:42, another 8 minutes. Tell us how it feels.
Sir,
Yeah.
what is the difference between the linear regression and polynomial regression? That like,
It is a function of x square.
okay, so like we're not fitting a polynomial, but we are fitting a linear function to a polynomial.
We are not fitting a linear function.
Okay. Okay.
We
Okay.
are not fitting a linear
Okay.
function.
Sorry. Yeah. Sorry. Yeah. Sorry.
We are fitting a polynomial to the. Okay, dear all, please mark your attendance. This is Akula's message. I will work it out tomorrow just to let you know what the final form is. I will write the final form. You're supposed to get this. I'll work out tomorrow. Don't worry. Don't get scared. You will be able to get it. If somebody already gets it in the next couple of minutes, it's great. Other people, don't worry. If you spend another 10-15 minutes, you will all get it. It is not rocket science, so, but no problem. Rocket science also we can teach you. Huh? It is very nice. It's a beautiful system of equation. Final system you get like this. Not bad. Out of 100 people, 75 people are there. Some 4 people we lost out. I don't know what happened. Oh, very good. Subhash, you got it?
Yes.
Okay. Okay, very good. So, Pradeep, Nikhil, Vikas. Oh, very good. Pratyusha, super. Anand, very good. So, you're all learning Inverse very well. Shubham. Others were Shalu, Pratiksha, very good, very good. Okay. So it is nice now. See, for example, suppose I teach this. Suppose I teach this and okay, say y equal to a square plus bx plus c, and this is the equation like this. So it will be a pure mathematics or statistics class. So you see, somebody Anand said this anyway. See, I flipped it. My original proposal was to teach this and give the motivation. But now on the spot we changed. Today we did ulta, right? So I just posed the heat transfer problem. Now you will not forget this for your life. You will note there are situations where AX squared plus BX plus C is coming in thermal science. It will come in civil engineering, it will come in electrical engineering also. If that is the case, this will be like this. So eventually now so much information is available. If you want to know what is a polynomial regression, Google will tell you. But I think the key question, if you have to become a good scientist or engineer, is where is it coming? Why should I know this? Where is it useful in my subject? These are the kinds of questions you have to ask. Now we ask that question first. We took the slab problem with heat generation and figured out that yes, there is a case for polynomial regression, and we can do this. We can torture it further and make it ax cube plus bx squared, blah blah blah, all that. But beyond square, in a classroom environment, teaching as well as testing you will become difficult. Suppose I give a cubic, that will be only one question in the exam. Okay, 1.5 hours. If quiz also, there will be one question. That's all. And then if somebody makes a mistake, it's gone. It will be unfair. So at least there should be 2 or 3 questions in a quiz, right? Because somebody may not be comfortable with one. All right. But it's possible to extend this. So now you know that once you get this data, you can do sigma of all these blah blah blah, and then you can use some technique. Tomorrow I will teach you a powerful technique of the Gauss-Seidel iteration, where you don't have to do matrix inversion. I will teach you the Gauss-Seidel iteration tomorrow, the algorithm at least, so that when you encounter a problem of polynomial regression, you will be able to solve it. Okay. Plus, but whenever you're looking out, you see where polynomial regression is occurring in practice, linear regression, how an economics fellow will apply, how a marketing fellow will apply. So just keep on thinking, right? Just talk to people who are outside your, talk to some friends who are not doing engineering. Okay. Talk to somebody who is not doing, talk to somebody, some of your classmates who is doing MBBS. Ask them, hey, what is the data you're dealing with? Yeah, I'm learning some inverse course. What is the data? Do you have any problem? You want to analyze data? You just talk to, please talk to others. Okay. All right. So you may get some ideas. So maybe along with your friend, you can do something. Okay. Oh, okay. On that note, we will end the class. Tomorrow, 10 o'clock. I will log in at 9:55. See you.